So there are a couple of prerequisites for this one. Pretty straightforward. You need to know the area of a circle is pi r squared, where r is the radius, not the diameter. And the volume of a cylinder is going to be the area of the base, in this case pi r squared, times whatever the width or the height is right there. So what we're doing today is we're doing what are called solids of rotation. And what that looks like is it looks something like this. So we have an area, and what we're doing with that is that we're rotating it all the way around, sometimes the x-axis, sometimes another line. We can also do this with the y-axis. Same idea, pick it up, rotate it around. But in either case, what we're looking at is we're looking at a situation where we're taking this area and we're going to have our same sort of infinitely thin rectangle here. But rather than having an infinitely thin rectangle that has, let's say, a square coming out of it, like that, so that the line that we draw is one side of a square, that line is going to be rotated all the way around so that it's forming basically the radius of a circle right here. So if we continue that all the way around, you can see that this red area that's under here, a sample rectangle from the x-axis up to the curve, has formed this radius going all the way around right here. And so what's happening is that when we have a volume of a solid of revolution or a solid of rotation, we have these little infinitely thin cylinders that we're finding the volume of and then adding up all those infinitely thin cylinders, starting all the way over here and ending all the way at that big end of the shape. So this is very, very similar to what we did in the last lesson, except that in order to find the area of the base before we find our dx or our dy and take the integral, the area of the base is just going to be a circle all the time, and the radius of that circle is going to be whatever that little height of the rectangle is that we find when we find area. So let's write down a few notes for how we do the volume of solids of rotation, and then we've got a couple example problems, and that'll be it for the day. So volume of solids of rotation. So these are created by rotating a shape around an axis. These are actually really useful for things like curvy table legs that you'll see, where they're the same if you rotate them all the way around. It's actually something that's used in manufacturing a decent amount. It's a pretty useful thing to be able to find the volume of, just because solids of rotation exist in a lot of places. The first thing we're going to do is we're going to draw the area that's going to be rotated. This is exactly the same as how we've done this in the past. What's slightly new is we're going to mark the axis of rotation. We're going to draw the infinitely thin rectangle. It's always going to be perpendicular to the axis. Then we'll label the height and width just like we would for area. We'll set up our start, stop, and dy, dx. And then finally, we'll use the little height as the radius for the area of the base. And for this one, the area of the base is always going to be pi r squared. In the equation, volume is the integral from whatever the starting value is to the stopping value, area of base times width. Again, this width is still dy or dx. So let's start off with a sample problem. First, we're going to find the volume of the solid formed by rotating the area bounded by the line y equals 3x, x equals 1, and the x-axis. We're going to rotate that area around the x-axis. So let's start by drawing that. So here's the line y equals 3x. Here's the line x equals 1. Here's the x-axis, and I am going to mark my axis of rotation. I'm going to do that in blue. You can do it in whatever color you want, but it should be pretty clear that right here is our axis of rotation. So our infinitely thin rectangle, let's see, let's mark the area. So the area that we're interested in is right here. And our infinitely thin rectangle has to be perpendicular to what we're rotating. So there we are. This is going to be a dx. And then this height right here, I'm going to do the upper one. So this is, I'm going to call this f of x equals 3x, because I know that as soon as I have that d of x, everything's got to be in terms of x. This is the line y equals 0, which is the same as, let's call it g of x equals 0. So this height right here is the top one, which is 3x, minus the bottom one, which is 0, or just 3x. So now that I've got all those labeled, let's see what I'm doing with it. I know that I've got a dx, so I can set this up. That means my starting value has to be an x. This is where x is 0, we can see. This is where x is 1. And now all I have to do right here is I have to figure out what's in start to stop area of base times the width. Just have to figure out what's in the area of my base. And in this case, remember, it's not that there is a circle on top of this, so this is being used as the radius of a circle that we're going to sort of rotate it around. And you don't have to draw this, but I'm going to draw this over here just for those of you who like pictures. So basically what's happening with this is that this is all turning into something that looks kind of like this. If we've got the x-axis here, we've got this basically this shape that's being rotated around. This is being picked up, this line's being picked up, it's being rotated around the x-axis, and so is every single other rectangle. So like up here we've got this big rotation around, so that we basically have this big cone where each circle has a radius from here to here in the area that's being worked with. And we can see that the cross-section, the area of the cross-section is just going to be pi r squared, the area of a circle, with this distance right here being the radius. So we go ahead and fill that in just like it says. So area of base is pi r squared. r is this, so we have pi 3x squared. We can take that, plug that into our calculator, find that value. This one, of course, you could do by hand as well, but since the friendly calculator is sitting right here, we might as well do this. Pi, make sure in parentheses, 3x parentheses squared, comma x, comma 0, comma 1, 9.425. Okay, let's do a couple more of those, and that will be it for this lesson. Find the volume of the solid created by rotating the area bounded by the line y equals 1 and y equals x squared around the line y equals 1. So area bounded by, first thing we're going to do is we're going to draw that. There's y equals x squared. Here's the line y equals 1. So we're talking about this area right here. We're going to rotate it around the line y equals 1. So I'm going to mark that in blue. Okay, so that means my rectangles have to be drawn perpendicular. We can see this is going to be a dx, and we can see that this distance right here is going to be this upper function minus this lower one right here. So let's rewrite these ones. It's a dx, so everything's got to be in terms of x. F of x equals x squared, g of x equals 1. So let's do the top one. Careful, this top one is g of x. It's this 1. And then the bottom one here is x squared. Voila. Now we've got our d of x. We do need our bounds, so just like normal for our area, we're going to say we know that f of x equals x squared. We know that y, or g of x equals 1. So the intersections here are going to be when those two are equal. So x is plus or minus 1. So our bounds are from -1 to 1. We're setting up volume. So we're looking for that area of the base. We know that this is a solid of rotation, so this is being picked up and rotated. So if you want to draw that out, you don't have to. I like to. What this is going to end up looking like is it's going to end up looking like we've got this area kind of right here. And it's being rotated around this axis. So basically we're just picking this up and we're rotating it all the way around and doing the same thing down here and the same thing down here and the same thing up here and so on. So we basically get this little curve where we have a whole bunch of circles. We can see then that the cross section is a circle with a radius. That's the distance from the axis to this f of x equals x squared. So this little red part here is the radius. So we can do pi 1 minus x squared squared. Again, that's most easily done in the calculator. pi 1 minus x squared squared, comma x, comma -1, comma 1. Ta-da!